Welcome to our presentation on our app, Glitch TV. We decided to name it after another popular app that inspired us, which I'm sure you can take a guess as to which one it is. So this is our team. My name is Santiago Salas.
And I'm Sunny Liang.
And our unofficial third teammate, Stack Overflow, who I'm sure you've all worked with. We split our presentation into four main sections. First, we'll discuss the application choice, briefly describe the main idea behind the app. Then we'll go over the problems with the base application and what it is vulnerable to. Third, we'll review the security upgrades we made to the app, discussing what we added and the design analysis. Finally, we'll wrap things up with some demos of the app. We chose to do Project Type 1, which was designing an end-to-end cryptography solution to protect your data application from attacks. The application we chose was a very basic streaming app with a performance goal of 1 frame per second. There would be a streamer who would be able to stream their desktop to multiple clients. We wanted to work with some type of live feed because we thought it would be interesting and cool to learn about. We decided to stick to desktop streaming to make it easier to test locally in case the VM couldn't support a webcam. When we were deciding on the application, we thought these were the biggest threats to consider. The biggest vulnerability for the base app was that the video frames would be readable by anybody that can see the packet. The streamer also had no way of preventing anyone from joining, and anyone could impersonate the streamer. We listed some basic security additions we would use to address these problems to use as a start. As we listed a security addition, we would reevaluate the security of the app to get a more detailed list. The resulting list of problems is a more complete list of the vulnerabilities and efficiency problems we discovered during our reevaluations. The base app provided no data integrity and allowed replay and reorder attacks. Adding a simple key exchange was not enough since active adversaries could obtain a shared key to become a man in the middle. There would also be no forward secrecy with a simple key exchange. To address the problem we listed in the previous slide, we would only need a PKI and asymmetric encryption. However, using just these two components would result in a drop to the stream performance. With all these attacks and performance to consider, we now had a more complete base to try and design a functioning security solution. At a high level, the main thing we want to protect is the data itself. This diagram showcases the part of our security solution that focuses on just that. We have a program that is capturing frames of the desktop or screen, which it uses to create a screenshot image. Before the image is sent to the client, it is encrypted in a AES with OFB mode block cipher using a 256-bit symmetric key. The client then decrypts the message to obtain the screenshot, which is then displayed to the client to effectively show them a live feed of the streamer's desktop. After adding these security upgrades, our application behavior has changed slightly from the base version. It still supports multiple clients, but now the streamer also has the option to stream in two different modes. Public mode, which is the default, where anyone could watch the stream, or restricted mode, where only clients on a whitelist can successfully watch the stream. The client can join a stream as long as it's public or if they are whitelisted. If a client that is not on the whitelist tries to join a stream in restricted mode, they'll get a message letting them know the stream is restricted.
In our secured app, we use authenticated ephemeral elliptic curve Diffie-Hellman key exchange. This prevents eavesdroppers and active attackers from obtaining the secret symmetric key and brute force attacks on the key with a quantum computer. This also ensures forward secrecy by creating a new shared key with each session. We used AES with OFB mode using a 256-bit key to secure our stream data in transit. We also use HMAC tagging to provide data integrity of the stream data and to prevent replay attacks. We also assume a public key infrastructure is used to obtain and validate public keys. In our design, we use 3 cryptographic primitives. For asymmetric encryption, we use elliptic curve Diffie-Hellman with a 384-bit key and RSA with a 4096-bit key. For symmetric encryption, we used AES with output feedback mode using a 256-bit key and a 128-bit IV. We observed no significant performance gain from using a 128-bit key for AES. In this slide, we briefly explain how authenticated elliptic curve Diffie-Hellman key agreement works. First, there is a trusted server, such as a public key infrastructure, to verify the server and client's RSA public key. Then, the server sends their elliptic curve public key. Next, the client sends their elliptic curve public key and a signature of both the server and client's RSA public key and elliptic curve public key, signed with the client's RSA private key. Finally, the server sends a signature of the server's RSA public key and client's elliptic curve public key. We will now show the design flow of our application. The server and client uploads their RSA public key into a PKI. The server starts capturing frames. If the server is ran in restricted mode, the server will build a whitelist. The server listens for connections. The client connects. Both the server and client generates their ECDH key pairs. The client sends a byte string hello and its RSA public key. If the server is ran in restricted mode, it will check if the client is in its whitelist. And if it is, it will send a byte string hello along with its RSA public key. The client sends a byte string DHINI. Server sends its ECDH public key. The client creates a signature with the server's RSA public key, client's RSA public key, server's ECDH public key, and client's ECDH public key, signed using its RSA private key.
The client then sends its ECDH public key along with the signature for the constructed message. The server verifies the client's signature by recreating the intended message and verifying the signature against that. The server then generates a signature using the server's identity string, which is the bytes of the RSA public key in our example, and the client's ECDH public key. This is signed with the server's RSA private key. The client verifies the signature, and at this point, all the parameters have been exchanged and they both calculate a shared key. They use this to derive a key and IV for the block cipher. They also use the shared key to derive a session ID and an HMAC key that will be used for tagging. When the client is done, it sends a ready message to the server to let it know it's ready to start receiving frames. At this point, a cycle starts. The server encrypts a frame and composes a message consisting of the derived session ID, a component ID for the frame, and the encrypted frame itself. It creates an HMAC tag for this and appends it to the message before sending it over. The client verifies the tag to detect if the data has been tampered with. It then validates the session ID and component ID to prevent replay and reordering attacks. Passing all these checks, the client decrypts the frame and displays it. This cycle continues until the stream ends or the client decides to leave. If the server decides to stop streaming, the client is notified that the stream has ended. If the connection dies for the client, they get a message that the stream may have ended or that a problem occurred with the connection. For the server, they simply stop sending data. If the client leaves, it sends a message to the server first to let it know it's okay to stop sending data and to close the connection.
In this demo, the client will connect over the public internet and disconnect the stream on their own. In this demo, the client will connect over the public internet and the server shuts down the stream.
So now we're going to go through another live demo. This one's going to be done purely on the local network as opposed to the internet, which we showed in the last two slides. Before we actually run anything, let's run this little bash script. And what this does is it's just going to generate some RSA key pairs. We'll need those for the restricted mode test towards the end. The program also does accept command line arguments. There are default values set so that we won't have to pass in all of these just to do some simple tests. So these are the ones for the server, these are the ones for the client. Now let's actually start up the server. Let's start up one client. Now let's see that it actually supports multiple clients. Let's start up another one. And let's start up a third one. So I'm just going to move this around just to show that it is a live capture of the desktop. We did also add logging to both the server and the client program. We don't need this one anymore. By default, the logging is set to warning, so I'm just going to set it to debug so that we get some more stuff printing out. Let's also stretch this out to make it a little bit easier to read. So it just shows some information that was very useful to us when we were trying to debug this. We can set different levels if we wanted to. Debug has the most output, which is why I set for that one. And I think we're ready for the restricted mode test now. So to actually test the restricted mode, we just have to set the server to restricted mode equals true. And the default RSA keys that are used for the client program point to client 1. And so in this scenario, we're going to show that the server has a whitelist which consists only of client 1's RSA public key. And so client 2 will not be able to connect. Since the default arguments for the client program point to client 1, we won't actually have to pass anything extra for client 1, but we will have to specify the keys that client 2 will use. So immediately you can see right away that the server does some extra setup before it actually starts listening to connections. It's going to load the public keys in its whitelist, so it's only loaded one, which would be client 1's key. And client 1 was able to successfully connect. Now we're going to load client 2, which is using its own set of keys, but the difference being client 2's public key is not on the whitelist. So as you can see, no window popped up. Client 2 wasn't actually able to connect. There's also a message saying stream is running in restricted mode and only whitelisted users are allowed. if we look at the server's logs, we'll see that it loads client 2's public key during the initial part of the connection, but then it rejects it because it's not on the whitelist. And it closes the connection immediately. And so now we have a server that's only accepting the specific users that it wants to accept. And that's about everything. Thank you.
For possible future works, we can include many improvements. For efficiency, we can use UDP for transferring frames instead of TCP. We will continue to use TCP for the key agreement. We can use image differencing between frames and use lossless compression on it. For user experience, we could use a GUI. We could resize the stream window and add support for webcams. For security, we can use a real PKI or something equivalent. For compatibility, we can make it cross-platform.
To recap, we added some security features to a basic streaming program and discussed the reasons for doing so. Thanks for watching, everybody.
Thanks!